Bismillah ar-Rahman ar-Rahim. So, so one of the proposals to calculate the metric over wireless lengths is what we call expected transmission count. Expected transmission count, and what that is that we need to know if we send some packets from A to B, what is the expected number of times required on average to get the packet across from A to B. When we say the packet will get across from A to B, this implicitly means that B will be able to send to A, because we cannot send anything without acknowledgement, right? So, so in that case, the way we measure this metric, for example, is by saying, okay, so we will send N, capital N, different probes. And by probe, we mean like a message, a control message. This is not a data. A control message that gets sent from A to B. Okay? So we'll send capital N different probes. We received on this side from these capital N probes, N1 probes have reached B. We'll do the same thing on the other side. We send capital N probes, and A received N2 different probes. So now, what is the probability that I send one packet from the first time from A to B? And we have calculated this probability to be, so this is the probability. So probability that from A to B, and from A to B we mean like two directions, right? Because we send and come back. A to B, given that the number of transmissions, equal 1. Which means that we send the packet and from the first time it reaches B. What is that probability? And we said that this probability is simply the probability that the packet goes from A to B and comes back from B to A. Which is what? When we say and, this means that the probabilities are A multiplied. So this probability is actually N1 divided by N multiplied by N2 divided by N. It's the two probabilities multiplied. So that's easy. So this is from the first time. So what is the probability that we go from A to B, again bidirection, whereas the expected transmission or the number of transmission equal to? This means that we try to send the packet the first time and it fails. And then we try to send it the sixth time and then the next time and it passes. This probability is what? If we assume that this is P, this is the probability of success. What is the probability of failure? 1 minus P, right? So the first transmission fails with a probability 1 minus P, and the second transmission passes with a probability of P, right? Okay, so what is the probability from A to B, whereas the number is N, general? This is simply 1 minus P. You send it N minus 1 times, they all fail. So N minus 1 multiplied by P. Right? So okay, so now we have the probabilities at N equal 1, at N equal 2, which means that the transmission now is a random variable, okay, which can take the value of 1, 2, 3, 4, 5, 6 to infinity, right? And the probabilities are like this. What is the expectation of any random variable if we know that the probabilities of this random variable taking different values is this? What is the expectation? The expectation is, so we're getting into some probabilities now. The expectation is simply is to say, so the expected transmission count equals now the value of the random variable. The value of the random variable is 1, 2, 3, 4, 5, and so on, right? So it's n multiplied by the probability of taking that value. What is the probability of taking the value n? It's 1 minus p to the power n minus 1 multiplied by p. And then the expectation is to get the summation of this on all values of n. So that's the expectation, right? Right? So now we need to get this summation.
You multiplied by n here?
N is the random variable takes the value 1, 2, 3, or n.
Yeah, which is power, but why you multiplied?
This is the expectation. The expectation of any random variable is the expectation of any random variable x equals x multiplied by probability of x. Okay? And then you do that on all possible values of x. So this is the expectation. Okay? So so we need to get this summation now. So we'll get into some algebra. So we have two choices. Either I give you this as an exercise and you get you know how to calculate it, or we do it together now. What do you prefer?
Let's do it together.
Let's do it together. Is it too difficult? So as we said last time, the problem with this is that this is not a direct geometric series. We know how to get the summation of any geometric series. Any geometric series is like, it starts with a value, let's say p, and then all the other items, they get multiplied by a fixed value. So it's any geometric series is like, it starts with a, and then the next one will be a times r, and the next one will be a times r squared, and so on. We know how to get the summation of this. This is very easy from algebra, from a basic algebra. We know how to do this. The problem with this is that there is n here. So n here is a sequential series. It's not a geometric series. So how do we do this? How do you get this summation? Well, so what we could do simply is that so again what we need to do is to get the summation of n equal 1 to infinity of n times 1 minus p, n minus 1 times p. This is the expected transmission count. Okay, so the idea here is simple. Just multiply all the two sides of the equation by 1 minus p. So it's we multiplied by 1 minus p times expected transmission count equals multiply 1 minus p in this summation. So this means that each item will be multiplied by 1 minus p, right? So this is equal from n equal 1 to infinity n 1 minus p to the power n multiplied by p. Okay, so which side is bigger now, the ETX or 1 minus p times ETX? Which side is bigger? 1 minus p. Huh? No. Which of these values is bigger, the ETX or 1 minus p times ETX? This is a very easy question.
1 ETX bigger.
ETX is bigger, okay. So we will subtract ETX from the other one. Subtract ETX minus 1 minus p times ETX, right? Okay. And we'll subtract the two sides. Okay? So this is 1, this is 2, and we need 1 minus 2. Okay? So you multiply this side, you subtract this side and this side, and you subtract this side and this side. Remember, if you this is if you try to expand this summation, this is P. If n equals 1, this is 1, and this is 1 minus 1, which is 0. So the first item is P, right? The second item is what? When n equals 2, this is 2, 1 minus P, right? Plus 3, 1 minus P, 2, P, and so on, right? Let's expand this. This is what? This is, and when n equals 1, now it's 1 minus P times P, right? Which is this without the 2. Plus, when n equals 2, that's 2, 1 minus P square times P. Okay, so when you look at this and you look at this, it's the same, but this is 3 and this is 2. And so on. Right? So when you subtract the two equations, you get simply 1 minus P. Right? So that's a P multiplied by ETX. Right? So this is the left-hand side here, subtracted from the left-hand side here. Right? Are you following so far? Equals this subtract this from this. P here does not have any corresponding value. So P minus 0 is P. Right? So here, this one is identical to this one. So 2 minus 1 is a 2 minus 1. And this is a common. So the result will be 1 minus P multiplied by P. Right? Plus, this one is similar to this one. This is 2 and this is 3. So it will be 1 minus P square P plus, and so on. So this is a geometric series. Why? Because you can see that the n has disappeared. The n, it was really causing problem here. So that's one thing. The other thing is that this can actually go with this, with this, with this. So it becomes much simpler now. So this will become, so ATX will become 1 plus 1 minus P plus 1 minus P square plus 1 minus P cube, and so on. This is a geometric series. We know how to get the summation of this. It's very, very easy. It's simply I don't know how to. I don't want to flip the page, but anyway. Okay, so let's do this. So any geometric series with a multiplicator of r, so it's basically 1 r, r square, r cube, and so on. The summation for it, given that r is less than 1. This is an infinite series. The summation for this is 1 minus 1 minus r. The summation is like this. which is very simple. So the expected transmission count. If you don't believe this, you can actually again multiply this equation by 1 minus r again and subtract, and you will get the same thing. So the expectation will be 1 over 1 minus, what's r here?
1 minus p.
1 minus p. So this is equal 1 over p. That's it. What's p? P is the probability, which is n1 multiplied by n2 divided by n squared. That's P. Okay? So this is the expected transmission count. So we do that every now and then. We send some probes, okay? And we calculate n1, n2. We get P. And then basically the expected transmission count is 1 divided by P. Simple as that. So if P equals 1, which means that every probe we send, it will reach to the other side. Assuming that n1 equals to n, n2 equals to n, in which case P equals to 1, in that case, the expected transmission count is 1, which means that whenever we send anything, we will get it through. Okay, so so given the expected transmission count, what is the expected transmission time? Okay, so if we have a link, actually we don't need this anymore. We can just remove it. So if we have any link with expected transmission count equals to 1 over 1 divided by P. What is the expected transmission time?
Depends on the speed and the size of the packet you are sending.
Excellent. So we can get the bandwidth of this link, again the current bandwidth, because again the bandwidth changes. So we get the bandwidth. The bandwidth gives you the time that you spend to send one packet over the link. The bandwidth. Basically, the time you send one packet over the link is actually 1 over the bandwidth. Right? So what is the expected transmission time? Is to multiply that by the number of times you send the packet, which is 1 over P multiplied by 1 over B, which is the bandwidth. So this is what we call expected transmission time. Because every packet you have to send it 1 over P times, right? And this is the time to send it once. So what is the expected transmission time? Is the expected transmission count multiplied by 1 over B, which is the bandwidth of the link. So if you have this, if you have a good accurate measurement of this from the physical layer, you have a good measurement of this from the MAC layer in the sense that you send some probes and you calculate the number of times that this probe actually can get on the other side, then you can calculate what we call expected transmission time. Expected transmission time will give you an actual representation of the cost or the metric that you can use to send anything across this link. The problem here with wireless is that you have to do that every now and then. You cannot just measure it once and expect it to be fixed all the time. So that's why in wireless you have to keep sending these probes, and you have to keep measuring how many of these probes get successful and how many of them fail and so on. And every now and then, maybe like every few seconds, every 1 minute or something, you have to calculate the expected transmission count, you have to calculate the expected transmission time and so on.
Even
Okay.
our topology is not changing. Even the topology itself is not changing. We should calculate.
Yes. Why? because even if the topology does not change, the channel changes. If one is passing by, the wireless channel gets affected, right? So this is the main challenge with wireless in general. Okay. So that's another way of measuring the cost over a link. There are multiple proposals. We mentioned round trip time. Round trip time is easy to measure. Why? You actually send a packet, you receive the acknowledgement, you have the start timestamp. Once you receive the packet, you have the arrival timestamp, so you get the round trip time. But again, this round trip time changes. So what people usually do is that they measure the moving average of that round trip time. But this is easier than expected transmission time. So the moving average of any value is actually so round trip time is you measure the current round trip time, and you measure the previous average, the previous historical average, which is round trip time average. Okay? And then you multiply this by alpha, you multiply this by 1 minus alpha. This is the moving average. So at the beginning, your average is 0. So you measure the current round trip time. You multiply it by alpha is any arbitrary number. Then this will be the new average value. The next time you measure round trip time, and you use the average here. So you keep doing that iteratively, and that's how you calculate the round trip time. So as the dynamics of the link changes, then you have a current measure of the round trip time. So why people? So there is a paper that I posted on Blackboard that actually claims, or they conclude that the expected transmission count will give you a more accurate estimate of the cost over the link. And in fact, the routing protocol, if it uses expected transmission count, you can actually get a better capacity on the network as a whole.
Both of them, FTT or ETT, both of them, they define the quality of link.
True, but in a different way.
Yeah, يعني if one administrator network want to see the quality, he can change ETT or RTT, or can
Right.
use both.
No. You have to unify the metric in the entire network. The cost over one link has to be estimated using one particular mechanism, whether it's round trip time or the problem with round trip time is what? The problem with round trip time is that it kind of lump sums the time required to send the packet to the other side, plus the queuing time on the other side, plus the queuing time on sending the acknowledgement back. So it kind of lump sums the multiple delays, if you will, in one value. This is not an accurate way of measuring the quality of the link. Why? Because the quality of the link is actually measured by the dynamics of the channel. But if you incorporate the queuing delays and the queuing state on each link, this queuing state doesn't have anything to do with the quality of the channel.
And it changes.
Yes, the queuing state depends on the application. Whereas we want to measure the quality of the channel, not without depending on the application. This is the problem with round trip time. Round trip time, it doesn't distinguish between the delay you require to send over the link or the delay required for queuing and doing anything inside the node itself. That's That's what RTT gives you. And you cannot, using RTT, you cannot separate the two. Some people, they try to enhance this by saying, I will not measure the round trip time. I will measure the, so I will send like, let's say, these are the two nodes, A and B. And instead of sending a packet, one packet, and waiting for the response, what I'm going to do is that I will send one packet, and I will send the other packet. So as per two packets, B here will measure the difference in time between the two packets. And then we'll send this to A. So in that case, you can easily, because when you send this, you process it in the queue of B, right? So B here has a queue. This packet will be sent here, and then it will get in the queue. And this packet will be sent later on, and will get into the queue. When you subtract the time for this packet from the time for this packet, assuming that the queuing delay is the same on average, right? So this will eliminate the queuing effect.
So assuming in delay, queue delay is fixed.
Assuming that the queuing delay or the processing delay, yes, is fixed.
But it's a strong assumption. It can be vary according to the algorithms that's used as a receiver to transmit the packets.
True, but يعني in a very short time, you can assume that the queue state will not change that much in a very short time. The assumption here, which you refer to as strong assumption, and I agree with you, is that the changes in the channel will be much faster compared to the change of the queue state. Okay, so that's again an incremental enhancement compared to the round trip time. So if you don't want to, if this assumption is not accurate or is not true, then go with the ATT, expected transmission time, in which case you have to calculate ETX, and you have to calculate the dynamic bandwidth, multiply the two to get the ETT statistically. Okay.
Question.
Sure.
You said that TTL is application level.
Sorry, what?
Time to live or what?
Yeah, the round trip time, you mean?
Round trip time is application level. So ETX.
It's
and
transport layer level,
So
yes.
it's on the Mac level or
Hardware
level?
Well, you send these probes. From the routing layer point of view. Okay, so the MAC layer will manage this at the MAC level by saying, okay, I will have to schedule this packet or this frame to send it to the to B. Okay, and then you calculate the whole round trip time again from the routing layer perspective.
So it has its own calculations.
Right. So as part of the routing layer protocol, you have to make sure that you send these probes every now and then. Okay, and then you calculate the round trip time. The exact same mechanism can be done at transport layer level if you want to calculate this at the transport layer level for something. For example, TCP can actually use round trip time. In fact, TCP does use round trip time. Right? TCP does use round trip time to calculate what we call the timeout, and we'll talk about this later. Right? So again, in that case, you may actually need to send to send some probes, or you have to calculate it as part of sending the data packets themselves. So that's a mechanism. You can do it from routing layer. You can do it from transport layer. Very good. Sam, تعال. Okay. So that's the expected transfer matrix we talked about. So there is the issue of, which is what Ala referred to 1 minute ago, which is the multi-radio routing. So for multi-radio routing, we have the so each node will have the capability of using multiple radio at the same time. So each node has multiple radio at the same time. So you can configure the node to use different channels. Okay. So if you have the possibility to go from this node to this node to this node, you can choose to select here channel 1, for example, and here channel 2. So why is that? The problem with wireless is that if this communication uses channel 1 and this communication uses channel 1, what happens is that they do some interference. They interfere with each other, in which case the bandwidth, the actual theoretical bandwidth of the link, will have to be sort of divided between those two links. Right? Otherwise, as we talked about before, there is a concept of hidden terminal problem and exposed terminal problem, which prevents these nodes from sending at the same time. So if you send from here to here, which means you have to have an acknowledgement. You send from here to here, which means you have an acknowledgement. If you send at the same time to this node, UA, you have a collision. That's if you are using the same channel. So sometimes from the MAC layer point of view, the MAC layer will give you the flexibility to change the channel on the fly. Okay? So if this one uses channel 1 and this one uses channel 2, so this link can use the entire bandwidth without affecting this link. Okay? So far so good?
I thought that each node has its proper channels. So, for example, node 1 has channel 1, 2, 3, node 2, channel 1, 2, 3.
Right.
It's not the same channel, or it is the same
No.
channel?
Yeah, this node and as a result, this receiver will have channel 1, channel 2, channel 3, channel 4, and this one may have 1, 2, and 3, and 4.
Different channel.
No, the same. No, not the same. But what we could do is that we can set at different times, we can set this to channel 1 and this to channel 2. And then for later time, we can set this to 1 and this to 2, or this to 3 and this to 1. And we can do that on the entire network level. It's not per link. So we have to make sure that when we assign these channels on all the different links in the network, that we're doing that in such a way that gives us the maximum capacity. The maximum capacity will happen if you have no two links interfering with each other. So you try to set these channels in such a way that minimizes or hopefully eliminates any interference from these channels on each other. You had a comment.
Yeah, in the same time, different channels.
Yes. Yes. Unless these links are far from each other. If they are far enough, then the nodes are outside of the interference range of each other, in which case they will not affect each other. So if the links are too far, they can use the same channel without affecting each other. If the links are close, then they better use different channel. That's the general rule. But this rule, how do you apply it in the whole network? It's a very difficult exercise. Very, very difficult exercise. Not easy, and we'll talk about this.
I saw in same papers that, for example, node 1, the sender node two, it's for example relay. Three, it's destination. One use any channel, for example two. Then the relay will select the best channel, one or two, based on for example the ETT. It will compute the ETT. Then
Right.
it will select the best
Right.
channel. Then it will use to send it to
Right,
the
that this
destination.
is in a relay scenario. A relay scenario is much easier compared to this. The problem with this is that we're talking about an entire network, which could potentially have tens or maybe hundreds of nodes. So it's not a relay scenario. It's not a simple relay scenario if you have like one node sending to a relay and a relay sending to the base station or something. It's not as easy as that. Here we're talking about an entire network, which could have maybe 100 nodes. And these nodes are interfering with each other. So we have to have a channel management technique that assigns different channels on different links in such a way that eliminates or reduces the amount of interference from these links on each other.
Assigned channel, which means is it fixed? It's
No,
assigned
no,
channel.
no, 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 no. It depends on the traffic demand, because if this node has no traffic to send to this node, why do I have to bother about, you know, assigning channels and stuff for the traffic coming from here to here? I don't care. So I have to change and adapt myself to two things: the dynamics of the wireless channel, which changes a lot, which will change the cost, the SNR, and different things, and the traffic demand. The traffic demand, this node may have some demand to send traffic to different nodes, but maybe after some time this node will stop sending traffic. So the demands of sending the traffic from nodes to nodes change. So I have to adapt myself to all these factors, which is not an easy task. Okay, we didn't talk about channel assignment here. There are tons of work, tons of research work related to channel assignment for multi-radio and multi-channel systems.
I just want to ask here. I talk about the relaying effect.
Right.
You use relay.
Right.
Is it when you are using a big network, they are different relay? It can be
Right,
also
but
as a
there is some correlation between these relays. They affect each other.
Yeah, for
So
sure.
yeah, so
But we guarantee that the reception of the package will be, for example, better quality.
right.
Because it will receive for different relay or.
That's true. What you're saying is true, and some of these relaying techniques, they are sort of, you know, used in a way in channel assignment for wireless mesh networks, but it's not enough. So in channel assignment for wireless mesh network, the scenario is much more complicated, because you have from this node, for example, you have different possibility for relays. You can use this node, you can use this node, or you can use this node, right?
Yes.
So and it's not based on relaying, which means only two hops. Here you have the flexibility to even go this way, this way, this way. So it's multi-hop in general, which means that you can have 2 or 3 or 4 relays. So how do you manage? Because for relays, for single relays, I expect to have one future transmission over the next link, and that's it.
Yes.
But here for wireless mesh network is much more complicated, because we have 1, 2, 3, and possibly 4 different links. So the problem becomes much more complicated. And not only that, here we have different nodes sending to different nodes at the same time. So it's not simply a source and a destination. You have multiple sources and multiple destinations going on the same link at the same time. So for relay scenarios, they usually talk about, you know, one source, a relay, and a destination, which could be like a cell tower or something like this. Or sometimes they say, okay, so we have multiple relays.
Yes.
We have done quite a bit of work on that. That's not. This is complicated, but what I'm trying to say is that this is much more complicated.
Yes.
Okay, so the problem here you don't have to worry about routing much. Why? Because it's 1, 2 links and that's it. You just perform some relay selection. That's it. But the problem here is that you have to rely on routing a lot, because the best route, yeah. So so the main issue here is that routing will become much more complicated because the degrees of freedom have increased a lot. So now you have, like before, your combination or your different choices are, should I go on this link or I go on this link? That's about it. Okay. With multi-radio, the question is now, should I go on this link on this channel or on this link on this channel? So there is, it's like 3D routing, if you will. You have another dimension altogether, which is the channel. So this network has become like 3D network, if you can imagine, which is now the complexity of the routing protocol has become higher. They call it combinatorial complexity, is that you have tons, and not tons, like you have potentially millions of choices. So which one do you choose? Okay, so that's a difficult problem, and and this problem is NP complete, of course. This problem is NP complete, which means that as the network grows large, the complexity of this technique will grow exponentially. So the number of choices, the number of combinations that you have to go through will expand exponentially as the number of nodes in the network and the number of links grow large. Okay? So there is no magical solution to this. You have to come up with like lots of heuristics. Okay? So this was like a preparation for, because what we need to talk about now is that this is an example of one of the heuristics for these types of systems. So what multiple relay least, I don't know what Q stands for, SR routing, shortest route yani. Quality, this is like quality, this stands for quality. Channel quality, shortest route. Okay, so least channel quality, shortest route. Okay, and this is multiple relay, multiple radio. So what this protocol claims or proposes is to use an end-to-end cost calculation. Okay, based on this equation. Okay, so the idea is, if I have like one node 1 and another node 2 and another node 3 and another node 4, okay, and then you decide to use here channel 1, here channel 2, here channel 1 again, okay, so the weighted, this is what we call weighted cumulative expected transmission time. Weighted cumulative expected transmission time. Because the expected transmission time for the case of single channel is basically what? The ETT on this link plus the ETT on this link plus the ETT on this link plus. So as the number of links grow, the cost will grow, which makes sense, right? Which means that based on this cost, you have to adjust your route based on the shortest cost, based on the total ETT. But here, the difference is we are using multiple channels. So the cost is not simply the summation of all these costs. Why? Because this channel, the link here, uses a channel which is different from this. So in a way, the transmission on those two channels is what we call orthogonal, or they are not correlated, or they are not interfering with each other. Okay? So if you are using one channel, the end-to-end cost will be simply ETT here plus ETT here plus ETT here. That's it. But here it's a little bit different. So what this paper tries to propose is to say the cost is simply the total cost on all the links, as we did before. It's as if they are using the same channel. Okay? Plus the cost of the maximum cost using any channel. Okay? So for example, in the example here that we talked about, here we have 1, 2, 3, 4, and here let's say here we have ETT equals here we use channel 1 and the ETT equals 2. Here we use channel 2 and ETT equals, let's say, 3. And here is channel 1 again and ETT equals maybe another 2. Okay? So the weighted cumulative ETT talks about the fact that first you have to sum all these costs as if they are using the same channel, even if they are not. Okay? And then this second part talks about the fact that you take each channel in the path, like channel 1. What is the cost, the total cost for channel 1? 2 and 2. Right? So for channel 1, the total cost is 2 plus 2, which is 4. So the cost for channel 2 is 3. Which one is greater? For channel 1. You put the maximum here, which is 4, you put it here. And now you perform a weighted summation. Weighted summation. So multiply this by 1 minus beta and multiply this value by beta. And beta is like some kind of a weighting factor. Again, this is a heuristic. It's not, this is like based on some heuristic. It's not, nobody has claimed this to be the optimum. There's no way this can be optimal.
So what's the importance of beta? Why?
Beta is a weighting factor.
And why it's multiplied?
It's a configurable thing.
Why we multiply?
Why? Because, even if you're using two channels, even if you're using different channels, the number of hops has certain factor, right? But since you are using different channels, so the transmission on the channels that use different channel is not correlated. So you should not simply get the summation of all of them as if they are using the same channel, because they are not. So what this guy claims is that let's just get a weighted summation of the two. Very simple, very simple idea. And then we can set beta like by 0.5. And I can ask you to do this on NS2 and, on a network, change beta and see and that's what he did in his paper. Okay, so change beta and let's see the effect of beta on the performance of the system. Again, nobody can claim that this is optimal in any way. There's no, for optimal, you have to prove. You have to have an analysis and prove that this is optimal. But there's no way you can prove that this is optimal. So in that case, it's a heuristic, and you can come up with a heuristic and prove using simulation that your heuristic is better than his and publish. So that's the way it goes. But this is one example. That's what I'm trying to say. Because the problem, as I said, the problem is NP complete. It's combinatorially very complex. Okay, so you have to have a very simple way of calculating the cost end to end, and that's one of the proposed ways. Okay. Any questions? So all these ideas that I'm talking about, these are ideas in actual papers. Okay, recent papers. They are not very old. After 2000, yeah. And you can see, it's very simple, and you can just propose something and prove that it works and works better than the state of the art. In which case you can publish. Okay. So this is one example for multi-radio. Multipath talks about the fact that from one node, one source to one destination, we usually try to find the best path, right? Multipath talks about the fact that you should not try to find the best path. You should try to find best group of possible paths. Okay?
Send in parallel.
So you can use that in two ways. One thing is one possibility is to use one path and use the others as backup in case this path goes down. Okay? So you use one and use the others as backup. Or, as you said, you can use all of them at the same time, which is what they call a
broadcast.
لا, not broadcast.
Parallel.
Simultaneous transmission.
Load balancing. They use load balancing, which means that they send on all these paths at the same time using some load balancing technique. You can send here 1/3, 1/3, 1/3, but maybe they are not the same. They are not equal cost. Maybe one of them is the best. Okay, so send on this 1.5 and send on this 1.25 and then send on this 1.25, something like that. So you use some kind of load balancing technique.
Doctor, these are channels, multiple channels.
No, these are multiple paths, multiple end-to-end paths.
They have the same performance?
Not necessarily.
Okay.
Not necessarily. So here we'll not simply choose the best path in terms of end-to-end cost. We will choose the best 3 or 4 paths based on the cost. You see what I mean? So you will not select the path with the minimum cost and that's it. You will select 3 paths based on what are the 3 best paths based on the end-to-end cost. So you use these paths that in a form of a backup or using load balancing.
There are multiple nodes between S and D. So
Oh yes, yes. Here we have a network. In the middle we have a network of nodes and stuff. Okay. So multipath routing it seems to be attractive from the sense that it can use to minimize the disruption time in case that path fails, right? Or even if that path doesn't fail, we can use load balancing to kind of create some fairness on this path. Not to have one single path end to end carrying all the traffic and all the other paths are not utilized.
In case of congestion.
In case of congestion and things like that, it's good. But of course, nothing comes for free. You have to manage multiple paths for every single session, which is costly, right? Managing all these paths is overhead. Okay, so there is a cost that you have to pay. So you have to weigh the cost you have to pay with the gain. Okay, so we're giving you the tools to kind of address trade-off between cost or overhead and the gain that you will get in terms of backup or load balancing or something like this. And then based on the application, you can say, okay, I can pay this cost and get the gain or the profit that I will get out of it, out of something like this. Or the application does not actually require all this kind of robustness or something like this. So I can just use single path routing, single radio routing, and that's it. Okay. So without waiting for setting up the new routing path, if there is if there is a path that fails, I don't have to wait to establish another route, because establishing the route will take time, right? So imagine if the route that you are sending your traffic on fails, then you have to send a route request, wait for the reply, and wait for and acknowledge and create, and this can take few seconds. During these few seconds, your traffic either lost or delayed. Okay, but if you have this multipath route and you have another route in the routing table, so you can switch to it in no time and have no disruption to your traffic. So the drawback, another drawback here for multipath routing is very interesting now. Is of course, in addition to its complexity, which is we talked about, and we can acknowledge that it's highly complex. But the design or the effectiveness of multipath route depends on how disjoint these paths are. In other words, if you have one source and one destination, okay, and you have multiple paths, right? Physically, if you take a look at the links, maybe you have from this source to another node here, you have one common link, which is shared amongst all the paths. I will talk about an extreme. And then from this node, you have 3 possible paths. So in that case, you have the 3 possible paths go from this node to this destination, but all of them, they share this link. Right? When I do the path like this means that all these paths are not overlapping in any other link in the network, which means that they are disjoint. They are using different links from the network. You see what I mean? So in that case, if this link fails, what will happen? All the 3 of them will fail. So ideally, I would like this multipath to be independent, in other words, disjoint. Otherwise, the gain that I'm expecting to get out of it is not exactly the gain that I'm anticipating or I'm expecting. Because if they are joined in some points over the network, then they are not as efficient. But ideally, I would like them to be disjoint so that if one fails, it does not affect the other one. Otherwise, it defeats the purpose. I'm actually using these multipaths so that I can increase the robustness. If one of them fails, I can use the other one. But while actually establishing all these multipaths, I created some kind of joint links between them. So I didn't do anything. So the effectiveness of multipath increases by how disjoint these paths are. مفهوم كده? So some people, they propose some techniques to calculate the effectiveness through these disjoints. How do I quantify? How do I quantify this disjoint path? Okay. So, for example, I can calculate the number of overlapped links and use that as some penalty on the paths, on these multipaths. Okay, because if this link fails, then all the paths fails, which is not what I want. And I'm just trying to utilize this multipath route to increase the robustness of the system and create some kind of load balancing. But the gain is not sometimes as I expect.
Yes, it is for us, for example, we are working on data center architectures.
Right.
This is a critical parameter.
Right.
Failure rate.
Right.
If we are proposing architecture, we have to study this parameter before submitting any paper. We have to prove that this parameter is very low. For example,
what parameter are you referring to? The disjointment of the.
We have to prove that we have different paths we can use.
Right.
To have a robust architecture.
Right,
We
right,
have alternative paths.
right,
If one path is down, we can use others.
right,
So it is good architecture.
right.
If it is not studied and it is not proven, it is not good. Yani it is a critical parameter. We have to
In
study.
addition to different paths, disjointed points, disjointed links, or disjointed.
Right. So
links,
again, in
they
data
have-
centers, if you're relying on physical paths, which could be like a data bus or something like this, or an actual network link,
Yes.
or like wired link or wireless link or whatever, if you have multi-paths and then all these paths are again joining in certain physical link or logical link or data path or something like this or data bus, again you are creating a single point of failure.
Yes, of course.
So all of them will fail.
Yes, we have to have different disjointed.
Right. So that's the same idea here. So disjoint paths are good, but of course the cost for creating these disjoint paths is higher because you are consuming more and more links.
Yes, and complexity.
So it depends, yes, so it depends on, again, the application. If the application is very important and you need to, and robustness is a very critical issue, then disjoint path is the solution. You have no way around it.
We have to manage this complexity.
Right,
manage-
and you have to manage this complexity.
Yes.
And guess what? I mean, you are running a network, not all the applications, they require the same quality of service.
Yeah.
So that's another trick. So how do I provide this quality of service per session, per application?
Yeah.
So each application will have its own set of routes. Okay, some of them may have multipath routing, some of them may have single path, some of them they have multi-channel, some of them they have single channel, depending on the type of application and depending on the quality of service that you want to give to the application. Okay.
Okay, another question. In case of load balancing, we divide our traffic on three channels.
Right. Not three channels,
three
on
paths.
three paths. Yes.
Okay, and one path is failed. One path failed.
Right.
So we will.
That's something in our hands. We can
We can
redistribute the load, but again, we don't have to disrupt the traffic, right?
We will lose time and.
No,
so-
why?
Because it will change. If I send my traffic in one
You
way,
will load the other two links
Yeah.
more, right? But you will not disrupt the communication because the paths are already established. So all you need to do is just to drop the failed path from the load balancing technique, from the load balancing update.
Yes.
But
And update the weighting factor. For example, you say you have three possible paths, so 0.3, 0.3, 0.3. All of a sudden, one of them fails. Okay, 0.5, 0.5.
yeah, it will.
That's it.
But if.
But again, this happens in no time. You don't have to re-establish the route. That's what I'm trying to say. Right? Establishing the route is very costly. Why? Because you have to send the route request. Remember we talked about establishing the route? In source routing, for example, you have to flood the network. Send the route request. You flood the network. You wait for the route response to come back. Right? So flooding the network will be like broadcast. And then you wait for the route response in a form of unicast. So that's not an easy job. And it takes a significant amount of time,
You
right?
have to do it before making.
You have to do it before making the communication. But now, if any disruption happens during the communication, you don't have to do that again.
No, I think that we have to have a routing table. We could
Well,
have
the routing tables, they require some kind of, again, some updates, route updates. You have to send periodic route updates. That's another overhead you have to go through. So regardless whether you use flooding or route updates, again, the failure has to be reflected on the table,
Yeah,
right?
update, yes.
So route updates have to run again. And guess what? For something like AODV, if the route fails, even though you use routing table, but you have to rely on some kind of a route request, which again will try to explore all possible choices for the route. So it will send the route request to multiple nodes, not just the nodes that has or have a routing table. So this routing table may actually be maintained by different nodes. We talked about this last time. If you listen to the video, you will, because some routing protocols are proactive. They try to update themselves at every single moment of time. Some other routing protocols are reactive. So there is a compromise between the two. Especially again when it comes to wireless, this issue is critical, whether to be proactive or reactive. And again, that depends on the type of application and how frequent your application and dynamics of the system changes.
For the load balancing, we have to make the paths before.
No, before, yes, you have to make all the path. But the thing is, this happens automatically. For source routing, for example, that you flood the network with some route requests. You receive multiple responses, but we used to accept the best one based on the end-to-end costs. But now you don't have to accept only one. You can accept the best 3 or the best 4.
It's what mean.
Yeah, this is what multipath routing does. So you maintain in your routing table 3 routes or 4 routes, and you don't have to reject all the others. You don't have to select one and reject all the others. You can select 2 or 3 or 4 in the routing table, and you keep them in the routing table. Or backup says that to use it as a backup mechanism, it says that use the best one in the routing table and keep the others in the cache. In case of that best route fails, take one from the cache, put it in the routing table. This process is no time. It doesn't cost any time, right? You don't have to do the whole thing again, right? But load balancing, you keep all of them in the routing table. And when you see multiple paths in the routing table, you send one packet here, one packet here, one packet here, one packet here. That's what you do. So that's what multipath routing does. Okay? All right, so hierarchical routing, we talked about that before. So in a hierarchical routing, what happens is that a certain self-organization scheme is employed to group network nodes into clusters. The hierarchical route, because we have realized through multipath routing and multi-radio and things like that the routing protocol can get very, very complicated, especially when the network is very large. So hierarchical routing talks about the fact that let's divide our network into clusters. Have a cluster head in each cluster, and this cluster head will be responsible for receiving the traffic from the nodes in that cluster in order to send it to the other cluster. So there is an intra-cluster communication and inter-cluster communication. Any inter-cluster communication is facilitated through the cluster head. Inside each cluster, so you have a cluster, and here you have multiple nodes. And you have one node here to be the cluster head. So all the nodes inside that cluster, they will have to send to the cluster first. It's like an access point, if you will. Okay? And then any communication between two clusters have to be facilitated through the cluster heads. So these cluster heads have to be chosen in such a way that they are optimized inside that cluster and they can communicate to each other.
But it will be a congestion in this head node.
True, that's true. If that node fails, the whole cluster will fail. But again, that's what's happening in all the other networks that are around us.
Yes, I saw this.
So the idea is that wireless mesh network, to try to avoid all the complexities related to multipath because these are very, very complicated. So now we talked about many challenges. We talked about proactive versus reactive. We talked about how to calculate the metric on a link. We talked about multi-channel or multi-radio and multipath routing, and all of this actually they have to be done in a very dynamic environment where the nodes can move and things like this. So it's very complicated. So let's face it. I mean, in some cases, it might not be feasible. It might not be efficient enough to design any protocol to achieve all these objectives at the same time. It's very, very hard. So clustered topology or clustered networks again tries to simplify that challenge, is by saying, let's divide our network into, let's try to go back gradually to the thing that we understand, which is access point, and all the nodes are around it. They have to connect to the access point. Why? Because having the control in one node is always, is always good. يعني زي ما بنقول بالعربي كده المركب اللي لها رئيسين بتغرق. يعني having the control centralized within one node is always the best concept, or the best way, or the most intuitive thing, right? But again, how do we apply this on wireless mesh network? Because wireless mesh network is not designed in such a way, and that's the best thing that can allow you to achieve this. We do not have access points. I mean, we will not lie to people and say wireless mesh network is to get rid of access points, but then we're getting back to clustered, which is access point. But now these cluster heads could be a mobile node. So we're just trying to reduce the complexity back again by using a concept which is close to having an access point, having a centralized way of control, because that simplifies many things. Simplifies routing, simplifies the MAC layer. Again, we talked about centralized scheduling in MAC layer. Again, is if you are in a meeting and you do not have anyone moderating this meeting, what will happen? You see people talking all the time. No, there's no discipline. And if people are talking all the time, then for you, these are just noise. You cannot hear anything. But now, if you have one moderator, at least for a group of people, then you can control things much easier. That's what we use here to simplify routing, because end-to-end route is very costly and sometimes combinatorially very hard. So what we do is that we say, let's break down our network into clusters. So within the cluster we can use, which is now a small network, we can use any routing protocol that we talked about. Okay? And then we have a network, another smaller network of cluster heads. We can apply another routing technique to facilitate the communication amongst the clusters. So this is what we call hierarchical routing. So we can use intra-cluster routing protocol and inter-cluster routing protocol. This concept exists in just about every type of network, whether it's a data center or internet or anything. Right? Border gateway talks about the same thing.
Yes, I
Border gateway protocol talks about the same thing. In wired network, in the internet, and I cannot afford to have the entire internet as one unit of network. It cannot work. It's just not scalable. So hierarchical routing talks about the fact that you can use any like shortest OSPF or something like this inside an autonomous system and nominate one designated router to be the inter-autonomous system.
But it is not scalable, this routing, because it will cost in terms of time, latency, to reach a point that is not near two clusters that are far.
This may not be the optimal from the end-to-end delay perspective. If that's what you are referring to, then I agree. But it simplifies significantly the routing end-to-end.
Energy, yes.
The routing in terms of establishing the route. Here, if you establish a route inside a small cluster, then it's much simpler, right? But from the end-to-end delay perspective, then you might be right, because here I'm forced to have to send to the cluster head, even if I'm trying to send to that guy.
I I tried to work on this on data centers, but I found that it costs in terms of time, so it's not feasible on data centers.
Well, in some applications, it might be the only choice. That's what we're trying to say. I mean, it depends on the application. Again, you have to look at the application requirements. If the application requires very, very large network, okay, very, very large data center or any processing units, then, I mean, dealing with all these entities as one big unit is just not scale. It's just not easy. So this is based on the concept of divide and conquer. You know the divide and conquer? You know, if the problem is very large, let's divide it into smaller problems and deal with each problem. That's exactly what we're trying to say here. So divide and conquer is a very common concept in military, in anything. So the problem is big. Okay, so let's divide it into smaller problems. Okay, and let's try to fix one problem at a time.
Especially for heuristic solutions,
Especially
in big network.
In big network, yeah,
complexity.
it's
Exponential.
in big networks, optimization is not a choice. So you have to go with heuristics. But
complexity exponential.
but بالضبط بس but heuristics then depends بقى. يعني you can come up with tons of heuristics, but if you want to see whether this heuristic is good or bad, then you have to again compare it with some benchmark. So you may have sometimes to solve the optimization problem, even though it's exponential, but you may have to solve it and get the best performance, even if it's exponential, so that when you design any other solution, you compare yourself to the benchmark. So that's one possible way. One possible heuristic is just to say, okay, so let's divide the big network, let's divide the big problem into smaller problems and deal with these smaller problems. And then, okay, so we'll solve it in an optimal way and compare the two. If the gap is reasonable, then we can claim that we have a good solution. Sometimes this gap can be measured analytically, which is great. In other cases, it may not be feasible, in which case, I mean, we can resort to simulation or an actual experiment and try to get some estimation of this gap, so that we say that we are, compared to the optimal solution, we are that far, which is acceptable. So that's based on some tangible analysis, okay? So we can talk about, this is the last one. So we talked about multi-radio routing, multi-path routing. So geographic routing talks about the fact that you route based on knowing the location of the node, regardless of the channel state. Okay. So the routing is based on the fact that from a certain node, from a certain source node, you know the location of this node. You know the location of the destination. Location means that these nodes are configured with GPS or with any other localization technique. So you know the location here, you know the location here. Even if these nodes move, you know the exact location at any point in time. So that's an assumption. This is an assumption. You have to agree on that assumption. So at any point in time, the source knows the location of the destination. And not only that, it knows the location of every possible node in the network. Okay? So the question is, what is the best route? Well, to know the best route, we have to draw some virtual graphs between all these nodes, because we know the location, right? But usually, the routing techniques in that category of routing, they do the routing based on greedy algorithm. Greedy algorithm that says, I need to know what is the best forwarding node, okay, from these nodes, that will get me faster to the destination. Well, if that's the objective, then we know the locations, right? We know the locations of all these nodes. So the best forwarding node is to say, I'm gonna select the node which is closest to the destination, right? Because this is what will get me faster.
Faster, it means closest. Like-
Closest to the destination, right?
But
Not closest to me.
okay.
Closest to the destination, because this means that
Signal higher.
Yeah.
I will reach to the destination much faster, right? Because if I select this one, and this one, select this one, and then this one, if I can reach this one directly, I better send to it. And closest here might be بقى defined in different ways. Possibly, if I have, يعني there are some details to this. This node, is it closer or this node closer? So then you have to decide. This node is closer when it comes to the line between the source and the destination, since we're talking about location. Okay? This node may be closer if we consider the line, the direct line. Okay? Maybe this node might be closer when we consider the absolute distance, but not necessarily the closest to here. If you take power into consideration, this problem becomes more and more interesting. Okay? I want to reach to the destination the fastest way possible and with minimum amount of energy or power. In which case, this node definitely is better, because I can reach this node with less amount of power compared to this node. So if you take multiple factors into consideration, then this problem becomes more interesting. But again, one common factor here is that this concept is greedy based on one transmission, one relay only, one hop communication. I have no idea about what will happen next. I do not have an end-to-end picture. I'm trying to see which node is the best one that will get me to the destination, using only the location. Using only the location. Remember, I do not have channel state here. I do not have channel state. Okay?
I know just the next hop, not.
I know just that I can send to this node, 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 and I can send to this node. Which one of them will get me there? Faster with minimum power.
No routing table.
No routing table whatsoever. I don't need routing table. Okay? Just a simple cache here that tells me, okay, so last time this node was best. So I don't have to do this exercise. So
But it must be updated.
must be updated, of course. So so the problem about that is that you send to the next hub, you select the one which is best at this point in time based on greedy concept. But again, you have no guarantee of delivery because you do not have channel state. So simply, you can get to a situation where you route to this node, and this node is in a room
Disconnected.
which is disconnected from any other node. That's it. You're blocked. Cannot do anything. Okay. So you come to a dead end, and that's it. And that's because you do not maintain. You maintain the location, but not the actual channel state. Okay, so all the greedy geographical routing algorithms, they have this problem. There's no guarantee of delivery. No guarantee of delivery. If you want to guarantee the delivery more, or at least increase the possibility,
Build a table.
then you have
To add more parameter.
add more potential relay nodes. Chances are, if I relay the traffic, instead of selecting one relay node amongst all these possible nodes, I'm gonna select two or 3 or 4 is similar to load balancing. But again, for me, it's just a one-hop thing. I don't have an idea about what will happen next. But in order to increase the chances, again, in order to increase, not make it 100%, I will send to this node and this node, and possibly this node. Or I can just flood, or I can just say all the nodes within this region, please take this packet and try to deliver it. Okay? So increase the redundancy. Always redundancy is good from the sense that it increases the possibility of achieving your goal. In order to reach your goal with higher probability, use redundancy. Repeat things. Do things more and more. Even if that, even if that forces you to spend some time or spend some cost. But always redundancy will increase the probability of getting there. Even then, there might not be like 100% guarantee, but at least you are increasing the chances. And that's because, again, you do not have an actual channel state. The only way to guarantee this delivery is by creating what they call, I'm not sure if this is in this slide, it's in this slide. So we talked about partial flooding. Partial flooding, we say, we flood all the nodes within this area. Please receive this packet and try to send it to the destination. And instead of sending to one relay node. Because one relay node will not guarantee the ultimate delivery. Partial flooding will increase the possibility.
Doctor, if there is circular dependence, circular connection, what will happen?
No, there's no circular here.
No circular.
Why? Because I always have the location. I always know whether I'm moving forward or moving backward. So actually, loops can happen in previous types of routing, but not here.
Yeah, previous slide.
Yes.
And this is continuous, no?
No, this is geographic. Geographic, I know the location. I know that as I'm moving forward towards the destination or I'm moving backward. If I move backward, then I know that I'm going in the wrong direction. So I will not relay backward. Because I have the location of my current node, I have the location of the destination, and I have the location of every possible node around me. So I know that it doesn't make any sense to go backward. Right? So actually this could be good to overcome some kind of a mobility. Mobility does not affect this in any way, assuming that I know the location of every single node. As the nodes move, I have the snapshot of every location of every single node in the network. So why do I have to care about mobility here? As long as the GPS gives me accurate location at any point in time of every node in the network. I don't care. Move here, I don't care. Okay, so the mobility has no effect here. So the only way for you to guarantee is by creating what they call here here, is it here? So here it talks about a single path. So these approaches increase the communication overhead, of course. So partial flooding, of course, increase the communication overhead. So that there is a cost. Redundancy always has a cost, right? So there is an overhead. But I'm trying to increase the possibility of delivery. The only way for you to guarantee the delivery is by creating what they call planar graph. Planar graph, these graphs are, you have to, from the source, you have to know that you have the location of every single node, right? So you have to draw a virtual graph inside the source to know what are the possibilities for you to reach to the destination. So you have the location of every single node in the network, right?
Like the routing table here?
No, because the routing table, again, the routing table is a forwarding table. It tells you that if you are in this node, you want to go to the destination, so go to this. right? Here is different. Planar graph, you have to virtually create an entire graph for all the possible paths from the source to the destination. Virtual, it's like a virtual graph from the source to all the possible nodes to all the until you reach the destination. Then you will say, okay, this is a node, and I can go here, destination, this destination, or this reached a dead end. This node, based on the location of this node and the location of the destination, there is no actual transmission. So you have to extract the entire graph end to end, not just a forwarding table. No, you have to generate the entire graph at the source node. You have to do like a graph, like you have to generate the entire graph. Okay, so this is not based on single path greedy routing protocol. This is like an end-to-end. You have to have an end-to-end virtual graph picture. This is the only way for you to know that some paths will reach to a dead end. Some other path will reach to D through this node or this node or this node.
Based on location, we can know.
Based on location, yes.
How we can know if
You know the location and you know the maximum distance between each node.
maybe it is not based on distance. If the relay will submit the packet to the destination, it's not because they are too close, so the packet will be in the destination. It is not based on the distance. Sometimes yes, it is based on this. Sometimes not.
يعني هو
This drawback of this algorithm didn't take the channel state. Talk about channel state into
Yes.
consideration. Maybe close
distance, but not channel state. Distance.
And this drawback because maybe they lost the packets because of channels, not because of distance.
So based on the distance, but you have the entire graph now. You can choose whatever because you have the entire path, and you can even send the packet through all the paths at the same time. If you send the packet through all the paths, you guarantee 100% that unless you are totally disconnected from D, خلاص يعني أعمل لك إيه يعني. You are in two separate networks. What can I do? But the problem is that with planar graph, you know that if you send the packet through this planar graph, you will have to reach there.
And you will determine the state.
Unless you have no connection whatsoever with D. When you construct this planar graph, you send the packet through the entire graph. So some path will lead to nothing, and some path they will lead to D. So this way you have guarantee that you have to reach to D as long as you have any type of connection to D.
But I can't imagine that it will update this planar graph every 2 or 3 seconds because
Very expensive.
yeah,
True.
the failure is not it's not
True.
accurate, but the
So just imagine how complicated this algorithm is. You have to form this planar graph every now and then. It's just very complicated. That's why the single path or single hop greedy algorithms are more commonly used and are more efficient, even if they lead to no 100% delivery. Why? Because in many cases, this planar graph generation every now and then is just very, very expensive.
and the failure is not common. In 99%, it will reach the destination. The failure is not.
No, this guarantees the delivery unless you have no connection with D. Like if you reach all these paths, they reach to a dead end, not reaching D. This means that you do not have any direct connection with D. So it's not the problem of the planar graph. It's the problem of how the network is formed, right? It's not the problem of the planar graph. It's not the problem of the technique. But the technique guarantees
No.
that you will deliver this with possibility 100% unless you don't have access to D. If you don't have access to D, what can I do for you?
Doctor, I didn't hear your question, by the way. If there is acknowledgement here, I don't know if she asked about this. If
No.
there is acknowledgement, no
Mhm.
acknowledgement. And this-
Why there's no acknowledgement?
There is
The acknowledgement will have to go on another planar graph that goes from D to C.
Yeah,
to S.
from the S to D.
From
there is
each node, you have to do a planar graph to reach to any other node. So each node will have to do this planar graph.
Yeah, I mean, D will send acknowledgement to S
Right.
that received.
Yes?
So it will
I mean-
guarantee that if it is not received, so it will resubmit it again if some failure happens.
True, yes. So when we do a planar graph, S will do the planar graph to reach to D. D may actually have to do another planar graph to reach to S.
But
Ideally,
it's
it could be
the
the same if the network is symmetric. And we'll talk about this in a minute. Maybe the network is not symmetric. So what happens on one direction is different from the other direction. So in which case, D has to create its own planar graph to reach to S. D will become S, and S will become D in that case. Okay. So the problem with planar graph is that it guarantees, on the bright side, it guarantees the delivery if you ever have connection to D. But the problem is that they are too complex. So here, I'm not just knowing the local information about the local geographical area that I'm in. I have to get the entire graph end to end. I have to establish this entire graph. And it's just too complicated, especially if nodes are actually moving. But the single path, greedy algorithms, they are not affected by the mobility that much. Because you just need to select one relay. So you know the location of all the possible relays, so you can select one easily. Okay? So we'll stop here. لأن شايف الناس خلاص